Okay, so first of all, I want to thank the organizer to giving me the opportunity to be here today to talk about my work, and specifically, I will give a talk which is in continuity with the previous one. Somehow, I will tell you something more about the phase diagram of high pressure hydrogen. So this, as Carlo said before, is a very long time challenge which started in 1935 with a prediction with the hypothesis of Wigner and Huntington that it was a phase, a metallic phase of atomic hydrogen, which was hypothesized to be stable over 25 GPa. But interest in this problem, as all we know, I assume, rose in 1968 when Ashtorff actually predicted this phase, this atomic metallic phase of hydrogen, to be a high temperature superconductor. And I think that we are all here today because we have there was a very big success, which I call experimental success, which was the synthesis of actually a high temperature superconductor made of hydrogen anhydride, which is H3S, which broke the record held by cuprates for more than 40 years, for about 40 years. And they broke for almost 70 Kelvin, which is really a remarkable result. And I think that since 2015, the attention on hydrogen really rose and brings us today. But this challenge on metallizing hydrogen is much more difficult than what originally expected, because it's not at all, not even close to 25 GPa, the pressure required to reach this pressure. So in this presentation, I want to focus on the low temperature phase diagram of hydrogen, as also Carlo showed you before. This is a very schematic sketch, and we actually do not know very well what's happening between 300 and 500 GPa, and where this atomic, this holy grail for us physicists, this atomic phase will be stabilized, if it exists or not. And the reason why there is so much confusion is, as also Carlo mentioned, that we have a lot of different experimental results that seems in contradiction, at least apparently. So for example, there is the experiment from Ranga Diaz and Silvera, which is a remarkable result in which they show that at 495 GPa, hydrogen starts to be highly reflective, and so this could be actually the first time we see the metallic hydrogen. But then there is another experiment by Paul Aubert published in 2020, which also Carlo mentioned, in which they see, by looking at infrared absorption spectrum, that they see this sharp transition at about 420 GPa, in which the system stops transmitting infrared light, and they assign this to a metallization, which is reasonable. And then there is the experiment by Mikhail Heremets, which actually measured the conductivity and say that at about 360 GPa, we have the onset on conductivity, and then track conductivity up to a bit higher pressure, which increase. So this here is resistivity. So resistivity decrease means higher conductivity with pressure. And so here we have a very puzzling result. So let me a bit recollect all this in this qualitative phase diagram here. So we have this phase 3 that at 360 GPa starts conducting. And so we have an onset of conductivity. But if you look at the infrared spectrum, it remains transparent in the infrared spectrum up to 420, when suddenly becomes opaque. And if you look instead optically by just making photos of the picture, you see that you have a transparent spectrum. This phase is transparent below 300 GPa, then start darkening, becoming reddish, and then black. And it remains black up to 490 GPa, when it was observed to be shiny again, and not to be shiny. And so what actually is happening here? So you see these results seems to be in contradiction between them. And there is some issue also in pressure calibration, but it actually is not enough to explain the difference between these difference. For example, if you correct for pressure calibration, these two lines gets even farther apart. So this mismatch with pressure is not just a problem of pressure calibration. And so this is a very good opportunity for me and for us theoreticians to try to say something, try to do some prediction to see what actually is happening. And because, as Carlo mentioned, hydrogen is in principle the simplest element we can simulate. However, it's a very challenging problem because actually we require an accuracy in comparing energies of different phases to predict the phase diagram below 1 milli-electron-volt per atom, which goes beyond the DFT accuracy. And indeed, the other problem is that hydrogen is also the lightest element in the universe, and the quantum fluctuations are really sizable, and I will show them in the next slide. And they are so big that we have huge anharmonic effect even at 0 Kelvin, which completely reshape the phase diagram, as I will show. So to tackle the problem, what we did was using diffusion Monte Carlo, and we also relaxed the fixed node approximation to actually get even better energies. And we corrected finite size error studying systems bigger than 1,000 atoms, that for as long as I know is the record in hydrogen right now. So we really pushed toward the accuracy to predict a very good energetics for the static phase. And then to study phonons, to study the anharmonicity, we used the anharmonic theory, the self-consistent harmonic approximation, which is an anharmonic theory, which allows us to predict anharmonicity and quantum fluctuations at DFT level. We use the DFT belief, which is one of the best functionals, and for hydrogen. And so these are the phases we considered. Most of them have been predicted by Chris Pickard, for example, and the three of them which I'm going to talk, also C2C24, which is the candidate for phase 3, CMCA 12, which was proposed as another candidate for phase 3, and CMCA 4, and these all three, I think, were predicted by Chris. And so then we have the candidate for the atomic phase. And here the gray dots you can see are snapshot of the quantum probability wave function of nuclei. And so that's why I say that quantum effects are sizable, because you can see them by eye. So as you can see, hydrogen, even at 0 Kelvin, are not static at all. And so to go to the main slide of my presentation, this is the phase diagram we were able to simulate by coupling diffusion Monte Carlo with this anharmonic theory that is the self-consistent harmonic approximation. So this is hydrogen. I plot here the enthalpy of each phase versus the pressure, and the phase that is stable at each pressure is the phase with the lowest enthalpy. Each phase has a finite line width, which is the error of finite size effect on the diffusion Monte Carlo calculation. And as you can see, what we find is that below 410 GPa, this most stable phase is C2C24, which is phase 3. Then we predict a phase transition to another phase, which is the CMCA 12, which we call phase 6. And then only at a much higher pressure than what was taught before, at 577 GPa, this phase 6 finally transforms into the atomic metallic hydrogen. And the reason why the atomic metallic hydrogen is stable at much higher pressure than even taught before is due to the anharmonicity on the quantum fluctuation. And you can see here, this is what also Carlo was showing before. If we neglect phonon fluctuations at all, the atomic structure is not even present up to 700 GPa. If we include quantum fluctuation at harmonic level, then this phase 6 is completely canceled out by the phase diagram, and we have just a transition between phase 3 and directly the atomic phase at about 486 GPa. But then anharmonicity push up again the atomic phase and makes the phase 6 stable again. The other important result to take home from this slide is that we also were able to simulate deuterium, and so the isotope shift. And for example, we predict that there is a quite remarkable isotope shift for the atomic simulation, so which goes even to 640 GPa in deuterium, the transition, which is quite far and probably quite difficult to reach in the very near future. But for deuterium, for the phase 3 to phase 6 transition is actually way better, because it's 442. So just 32 GPa of isotope shift. Now remember this number, 32 GPa, because it's interesting, and we will see later why. So as also Carlo mentioned, the main point here is, okay, we predicted the phase diagram, but there are a lot of ways of predicting phase diagram. How can we sure that this is the exact one, this is the correct one? And the answer to this question is we need actually to predict which are the experimental signatures to each one of these phase transitions, to compare with the experimental data we have, and to propose eventually new experiments to confirm this. And so the best way to do this is optical experiment, for example. And we predicted the optical properties of the system. And as you can see, this is phase 3. So we predict by accounting for quantum effects, also the indirect gap, which is this line here, which we show it closes at about 370 GPa, which is in quite good agreement with the onset on conductivity observed by Michaela Hermetz and group, and which can be seen here. Which so we are able to. So what does it mean? It means that actually the onset of conductivity observed experimentally is not a phase transition, slightly speaking. It's still phase 3, but we have just the band gap that is closing with pressure. Then the optical gap, which we measured by measuring the transmitted spectrum, so exactly like it is done in the experiment. So we measure transmittance on the sample and just take where the instrument precision, is not able anymore to see anything. And we say this is the optical gap. And it's in very good agreement also with the data from Laubert, up to a certain point when Laubert observed this drop here, and we will see this later. And this drop, we can prove that is associated to the transition to the phase 6. And actually, we can measure again the transmittance of phase 6. This is the CMCA12. And what we observe is that the transmission dropped before the C2C24. So this is at 355 GPa, and already at 355 GPa, the CMCA12 is almost completely dark. So this means actually that if you want to see a transition between phase 3 to phase 6, actually in the infrared light, here this optical spectrum, you can see a drop of the transmitted light, exactly like it's observed in the Laubert experiment. And the pressure agrees remarkably well. We observe 410 plus or minus 20 GPa, and you observe 425 GPa, so it's quite good, the agreement. We can propose an alternative way of measuring this phase transition, which would be very good if we can have experimental data on this, which is a jump in the conductivity. So we expect that on the transition, conductivity, static conductivity will increase by a significant amount. And this could be measured because conductivity measurements at similar pressure are already available. And so I think this is something that probably will be available in near future and will be an independent way of proving that actually there is a phase transition to phase 6. Then the point is that one of the points is that as I show you in the previous diagram, if you look at the optical spectrum in the visible light, you don't see any difference between phase 3 and phase 6. And this is can be seen here. So at 460 GPa, for example, the reflectivity for the C2C24 and the CMCA12, which are phase 3 and phase 6, are almost identical. And they appear, here I made a photorealistic rendering by just integrating the optical equation with the simulated refractive indexes, imaginary and real refractive indices of the phases. So you can see here that this appears as a black metal, as a black metal, and as we increase pressure, we start increasing a bit the reflectivity, but not so much that is really visible until really high pressure when we transit into the atomic phase, which is this one here, when the sample start shining. So actually, looking at the reflectivity is a good way to detect the atomic transition, and the problem is that our pressure do not agree very well with what observed by the experiments, and so now I told you that we are able also to do the isotope shift, and we have an isotope shift between the phase 3 and 6 of 32 GPa. And last week, Paul Aubert published finally a paper, so in which he remade exactly the same experiment, but with the deuterium, showing a isotope shift of 35 GPa. And so this was a prediction, because our paper work on archive was on archive already on January. So our prediction agrees very well with the data. And so this is a remarkable result, I would say, which makes the data even a bit more trustable. And so that's why I'm really confident that this phase diagram is actually a very good one. Yeah, I have finished. So to summarize a bit what we have done, so we predict the existence of phase 6, which is CMCA12 above 410 plus or minus 19 GPa. And this phase transition can be detected experimentally looking at low energy excitations like infrared optical spectrum or DC static conductivity measurements, which would be another proof of this phase transition. And we predict a 32 GPa of isotope shift, which is in very good agreement with and confirmed by experiments very recently. And for the atomic transition, we predict this phase transition to be stable at much higher pressure. And this is a robust result, we think, because with respect to harmonic, the reason why the pressure is so high is essentially that an harmonicity lower a lot the vibrational energy of the H2 molecule, while in the atomic hydrogen is much more harmonic. So when an harmonicity is taken into account, it favors molecular phases. And therefore, the transition to the atomic phases is shifted to higher pressure. So that's the reason why. And so reflectivity measurements are a good way to detect this phase. And so it remains an open question is, what is the phase observed, reflective phase observed at 500 GPa? And this is a very interesting question, because maybe another phase exists, which could be even superconductive, we don't know. So this is an open question, and I think it would be very interesting to investigate.
Thank you very much. Thank you for your nice talk. So we are ready for some questions. Okay, Sergio again.
The existence of this intermediate phase that you mentioned here, in order to prove that, you employ the self-consistent harmonic approximation, and you find a big harmonic effect within self-consistent harmonic approximation, which is an approximation and which try to fit an x square over, for example, x to the 4. And then there are drawbacks of this kind of approximation. How do you rely on this kind of approximation, since this is a crucial
So, okay, so the point is that even if it's called harmonic approximation, it's a theory which is able really to capture a lot of anharmonicity in a lot of systems, even when we have a saddle point energy landscape. And the reason is that it doesn't fit the exact wave function. What it does instead is use a variational principle of the free energy. So it's a theory which is targeted, whose target is exactly having a good estimation, a variational estimation of the free energy. And so even if the wave function for the nuclei that we have is not really exact, you should not look really at that wave function as an observable, in the same way in which in a DFT calculation you don't look at the single Slater determinant as a true wave function of the system, but the energy that you get is very good. In the same way here, the free energy is very good because it's approximated to a higher order. So this works actually very well for this kind of systems. So we have not only since it's variational, we have another great advantage, that is we benefit from error cancellation. And this is particularly important between the two molecular phases that if I show you once again, the CMCA12 and the C2C24 are very similar as the two phases. And so this means that error cancellation is expected to be very high between these two phases. While since it's variational, we expect that the error on the atomic transition would push the transition even to higher pressure. Because since molecular phases are more anharmonic, if there is something that we are not able to capture, it means the energy will be even lower with respect to the harmonic one. So if we make an error, we are estimating a lower value of the transition. So this will push the transition even farther.
Okay, another question from Lydia.
Oh, can I ask? Sorry, it's me. I wanted to ask, because you showed that for the total energy you were using this DMC.
Yeah.
And instead for the SHA you were using some B3 leap and so on. How much does it depend on the functional that you choose then? This
okay, that's
result?
a very tricky question. As Carlo mentioned, there is no perfect DFT functional, unfortunately, on hydrogen. And we choose the BLEAP because together with the van der Waals DF, which was talking Carlo before, they are almost the same precision. We tested them and we get a difference in energy of less than 0.3 millielectron volt per atom, which is below the accuracy we have with, for example, DMC finite size error. So we try to use the best DFT functional available for the DFT. This is not yet perfect because, for example, I do not have the slide here, but we also computed the spectroscopy, so the vibrational spectrum with full anharmonicity, so we are able to estimate the lifetime and so on. And what we observed that after we put anharmonicity, we still underestimate a bit the H2 vibrational frequency. It's very close to experiment, I have to say, so that's somehow a benchmark that is working quite well, but it's still a bit lower estimating. So there could be an error, which is quite difficult to estimate.
Last thing, how do you do relaxation? So you do relaxation in DMC and
we did the relaxation with the anharmonicity. So to compute this, and for the atomic phase, we fully relax all the internal degrees of freedom. But for the molecular phase, we did the relaxation at the anharmonic level. So this means that we take the average position of atom after anharmonicity and quantum effects are included, which change indeed the bond length. And then we use those reference structure to compute the difference in energy between the DFT calculation and the DMC with a lot of atoms and so on. And then we use this correction to correct on the DFT.
But then the DMC is done with a different structure than the anharmonic calculation.
The DMC, we corrected. So what we did, in practice, we computed the DMC for fuse structure to have very accurate results on the DMC at various pressure. And then we fit the difference on the same structure between the DFT and the DMC as a function of pressure, and we apply this correction to all the pressure simulated with DFT. So our results in this way are independent of the DFT function.
Okay, Peter.
Forgive me if you said this and I missed it, but is there a clear qualitative distinction between the reflectivity in the molecular phase and in the atomic phase?
Yeah, yes, there is. So, okay, this is the slide. So as you can see, so this is reflectivity versus the energy, actually. So this blue line is the atomic phase. This other line here is the phase 6. So it's the new molecular phase that should transit in the atomic phase. So there is when the system transits into the atomic phase, we have a jump toward higher value of reflectivity in optical reflectivity, and this should be a visible effect as reported in the photorealistic rendering.
I'm sorry, maybe I'm missing something, but if I'm doing an experiment, I don't think I can tell the difference between the blue line and the magenta line. They're both sort of Hagen-Rubens-like, and I don't see how you tell the difference. Maybe I misunderstood what you said, but you mean
these two lines here.
Yeah. I mean, in practice,
it's a bit like you can. So this is this is not. So the line you should see is this for the molecular, because unfortunately these are structure at the same volume, which for atomic and molecular doesn't mean at the same pressure. To compare the same pressure is here. So it's 560 GPa for the phase 6, which is this one, and this one here is at the more or less so it's more or less independent on the pressure, the atomic one. So you can compare these two. So essentially what means is by looking at eyes, telling the difference between this rendering here. So if you look through a camera, telling the difference between this and this, maybe, oh, sorry, maybe the slides doesn't show much of the difference.
Well, I'm not looking at the photographs. I'm looking at the curves.
Okay.
Yeah.
Between these two, so you have a reflective invisible light. You have 80% of light reflective versus 40% only.
Yeah, but the energy dependence is roughly qualitatively the same, and degrees in absolute reflectivity are always difficult. Yeah. Okay, just wanted to know. Thank you.
Yeah, no, but what actually must happen if you have a transition, you must see a jump, no? Because there is a strong difference between two. So you should see at a certain point that the reflectivity increase a lot. So that's why.
Is it everything calculated in independent particle approximation?
Sorry?
These reflectivity data are calculated in independent particle approximation.
Yes, but on the with including anharmonic effects and quantum effects on this with using phonon disordered structure. So we generate very big supercell of a system with,
but not on the electrons.
No, not on the electrons. So this is independent particle approximation. So this is I mean, we use the meta GGA, which is the modified Bailey-Johnson GGA, which has an accuracy which is close to the one of HSC06, which is, but I mean, unfortunately, it's not.
Yes, because Carlo showed just before that the GW0 are quite consistent with respect to quantum Monte Carlo simulation.
Yeah. I mean, we expect we made some tests, we compared, and we expect we have an error on the gap of 0.4 electron volt.
Okay.
So that's the error we expect.
Are there other questions? Okay, there is one in the audience. Can you open the microphone? I don't.
Yes. Do you see me? Well, I don't see much.
Yeah.
Okay. No, I wanted to understand how you do this optical calculation. When you compute, you say you compute the optical gap, right? In exactly the same way that Lubert, I mean, the same criteria of Lubert.
Yeah, we use this for the gap. We use the same criteria of Lubert. Yeah.
Well, transmittance or absorption is the same, I think, right?
Yeah.
So we found this of course, we use configurations, and we use HSC to compute the orbitals, and we compute with Greenwood, we compute the absorption spectra, and we found some difference instead. So I don't understand what is the difference in what you do with respect to, I mean, I don't know if you can comment, because
so that's a very tricky question, because, so I mean, what we actually are doing here, we are extrapolating the results we get from the SHA to a very large number of atoms. So we generate a system which have 400 and up to 700 of atoms randomly displaced randomly according to the self-consistent harmonic wave function. And then we take one single shot, because when we increase, we go to the thermodynamic limit, the error on averaging between different configuration becomes very much lower than other errors. So we just take one shot, one single configuration. We tested it on many configurations, and then we compute the transmittance using this meta GGA functional, the modified Baylor-Johnson, as done in standard code. So that's our procedure. So I think that we have some, and but without computing optical gap, and so now computing direct gaps, and so we just measured directly the electric constant, and then the refractive index, and then from the refractive indices, the transmitted intensity across the sample. So that's how we